Linear systems. Our objective for this video, we want to define a linear system, which is also called a system of linear equations. And we want to determine whether an ordered pair is a solution to a linear system. So what do we know coming in? Well, we know the general form of the equation of a line. That general form is ax plus by plus c equals 0. From this, we want to note that there is another way of writing the general form of the equation of a line, and we do that by simply moving the constant to the right side of the equal sign. So the constant on the other side, and another form, or another way of writing the general form, would be ax plus by equals c. Okay, so first off, let's define what a linear system is. A linear system, or a system of linear equations, is two or more linear equations working together. The linear equations are often written in the general form, and they would often be written in this version of the general form here. However, you'll also see those equations written in either y equals form or x equals form. And let's take a look. We're going to be dealing with two types of linear systems. One will be a linear system in two variables, also called a system of linear equations in two variables. And as with two variables, we'll use x and y. And as you imagine, we can graph this on a coordinate graph. We have x's and y's. We can graph this on the xy plane. We're also going to work with a system of linear equations in three variables. So we're going to deal with x, y's, and z's. And now we're and when it comes to graphing it, we're going to get ourselves into three dimensions. And so we're going to see the solution, but it's not something that we're going to be very good at trying to draw. Drawing and seeing something clearly in three dimensions is better left to computers, generally speaking. Okay, so an ordered pair is a solution to a system of linear equations in two variables if it satisfies both equations, and I want to underline the word both. It has to satisfy both equations in the system. Let's take a look at a couple of examples and see what that means. Let me slide this up a little bit. I think I got it. Okay, example 1 here. Consider the system. Well, the first equation is x plus 2y equals 2. And the second equation is x minus 2y is equal to 6. And I'm going to label these equation 1 and equation 2. Because I'm going to write them down here, and I want to make sure that you know which is which. And the question for letter A, we're going to use this system twice. Letter A, the question is the ordered pair 4, -1 a solution of the system? In other words, when x equals 4 and y equals -1, is that a solution to the system? Well, let's take a look at equation number 1, which is x plus 2y is equal to 2. Okay, and let's substitute. The ordered pair 4, -1, x is 4, y is -1. Let's put 4 in for x. Let's put -1 in for y. And the question is this true? Okay, does this point satisfy this equation? Well, you can pretty quickly see this is 4 minus 2. And so we wind up with 2 is equal to 2, and so we can put a check mark there. This ordered pair satisfies equation number 1. Okay, however, in order to be a solution to the system, it needs to satisfy both equations. So let's test equation number 2. Equation number 2 is x minus 2y equals 6, and we want to know, does the ordered pair x equals 4, y equals -1 solve this equation? Well, let's see. Let's put 4 in for x. Let's put -1 in for y, just like we did over here. And it's a question, is this a true statement? Well, again, you can probably quickly see 4 plus 2 is 6. So in this equation, the ordered pair 4, -1 also solves equation number 2. So we can make a note. The ordered pair for -1 satisfies both equations. Okay, it worked. It solved. It shouldn't say it solved. It was true in both cases. Okay, therefore, it is a solution of the system. All right, it has to satisfy both in order to be a solution to this of the system, and it did satisfy both. Let's do a second example, and we're going to use the same ordered pair. So I'm going to remind ourselves, I'm going to write that ordered pair. Let me get my notes together here. The ordered pair we were working with was x plus 2y is equal to 2, and I label that as equation 1, and x minus 2y is equal to 6, and I labeled that as equation 2. So is this ordered pair is different. Is the ordered pair -4, 3 a solution of this system? Again, x is -4, y is 3. Well, we need to check them both. Let's check out equation 1, which is x plus 2y equals 2. When x is -4 and y is 3, is this true? Well, let's put -4 in for x. Let's put 3 in for y, and it's a question. Are these two sides equal? Well, you can again probably pretty quickly see -4 plus 6 is 2. And so as far as equation 1 is concerned, -4 is a solution to equation 1. However, again, to be a solution of the system, it has to satisfy both. Let's check equation number 2, which is x, minus 2y is equal to 6. Well, let's substitute -4 in for x and 3 in for y. And we have a question. Is this a true statement? Well, this is -4 minus 6, and the left side is -10. And so, nope, -10 is never equal to -6. -10 is never equal to 6. So the ordered pair -4, 3 is not a solution to equation 2. Okay, it was a solution to equation 1, but not to 2. It has to be a solution to both in order to be a solution of the system. So let's make a note of that. The ordered pair, -4, 3, does not satisfy both equations. Again, it satisfied one of them, but when it comes to satisfying both of them, that didn't happen. It did not satisfy both equations. Therefore, it is not a solution of the system. And there you have it.